নষ্টই দিও দি মিনিট
এটা তো সেন্টারে খাইবে না আরম্ভ হইছে
দুটো খাইবো রে
chapter of your 11th class का chemistry, and it comes under physical chemistry. So today we are going to do till enthalpy, okay, and from that we'll continue in the next class. Okay, let's start. So what is the basic definition of thermodynamics? So thermo means related to your heat, and dynamics means the study of motion. So thermodynamics is heat in motion, okay, transfer of heat, how heat is being transferred from one place to other, that is studied under thermodynamics, right? So the chapter briefly covers the various important terms which are concerned with the transfer of heat and with the study of heat and heat energy, okay. All right, so the major questions in this field of thermodynamics is, how do we determine the energy changes involved in a chemical reaction and process? How do we determine whether it will occur or not? Next, what drives a chemical reaction or process, and to what extent does the reaction proceed? All these can be answered on the basis of thermodynamics by studying the heat changes. One thing we should be clear about, the zeroth law of thermodynamics. It says ki, suppose there is a body A. Okay, first thing, even before the zeroth law, the first thing which we should know is heat travels from hot to cold body. Okay, this is the basic principle of thermodynamics, that heat travels from a hot to a cold body. Now coming to the zeroth law, the zeroth law says if there is a body A which is in thermal equilibrium with a body B, okay, right, there is a body A. Thermal equilibrium means the temperature of A is equal to the temperature of B, and there is a body B which is in thermal equilibrium with a body C, right, then temperature of A is equal to temperature of C, which means that body A is also in equilibrium with body C. This is a very basic law which is called zeroth law of thermodynamics. Let's move on. We will now see the thermodynamic terms. Firstly, system and surroundings. Okay, system is that part of universe in which observations are being made, okay, and remaining universe is the surrounding, okay. This is the definition. The universe is equal to system plus surroundings. Entire universe other than the system is not affected by the changes taking place in the system. Therefore, for all practical purposes, the surroundings is that portion of universe which can interact with the system. So this is a more practical term, more practical definition of surroundings. Moving on, examples are not necessary. We'll just move on to types of system. And firstly, we have an open system. Okay, open system. Okay, all these types of systems are classified according to movements of matter and energy, right? Whether matter and energy, first is matter, second is energy, whether they can move in or out or not. Based on that, we have classified the systems. In open system, energy and matter both can move between system and surroundings, okay. For example is an open beaker, okay. Here the boundary is an imaginary surface enclosing the beaker and reactants, right. Then we have the closed system. In a closed system, there is no exchange of matter, okay, but exchange of energy is possible, right? So in an open system, both can be exchanged, matter and energy. In a closed system, matter cannot be exchanged, but your energy can freely be exchanged between system and surroundings. Example is a closed vessel, right, made up of a conducting material. Next, the third and the last system is the isolated system. Here, no exchange of energy or matter is possible. So, an isolated system, you cannot let the energy or the matter escape from the system, or you cannot let anything come from the surrounding also. Both of them cannot interact. That is the basic definition of an isolated system. Example is reactants in a thermos flask. Okay. Next, let's move to the state of the system. So, in order to describe the system, okay, state of the system means how the system is at a particular time. Okay, that is what the definition of state is. Like, we also use the term state for situation. Okay, so we can just say the situation of the system at a particular time is the state of the system, and it is, you know, you can determine the state of the system by using variables, state functions or state variables. Okay, we specify the state of the system by state functions or state variables. This is the practical knowledge you gain from the definition of state, how to determine, right? So the state functions are pressure, volume, temperature, amount or the moles and all. These are state variables. Okay, why are they state variables? The important part here is they are state variables or state functions because their values depend only on the state of the system and not on how it is reached. So you don't see the path here. Okay, state functions only depend on the initial and final position, we might say, or initial and final state of the system, we can say. It does not depend on the path. So it is independent of how you have reached that state. You could have reached that state through any means, like you could have taken a multiple routes, but it does not depend on that. The change in pressure, change in volume, all these are relevant. They are not dependent on how you have changed the variable. Next, we have one more state function, the internal energy. So when a system gains an energy or loses energy, that is change in energy. Okay, but there should be something which represents the total energy of the system. The total energy may be chemical, electrical, mechanical and all, but the sum of all these energies, okay, the sum of all these is the energy of the system, and in thermodynamics we call it internal energy, or U. Okay, how to change this internal energy? You can change it by passing in heat, you can change it by doing some work, or changing the amount of matter. So there are three ways to change the internal energy of the system. Another thing we need to know is that internal energy, enthalpy, these are your state functions. Okay, right. Next, we move to the work. Let us first examine a change in internal energy by doing work. So this is, they have explained a kind of work. Okay, we have taken an insulated thermos flask. Okay, this is an example of an isolated system, no exchange of heat. Okay, no exchange of heat or no exchange of quantity also. So, and this type of system, okay, it is called adiabatic, right? There is no exchange of heat, so it is adiabatic. We need to remember, right? An adiabatic process is a process in which there is no transfer of heat between the system and the surroundings. Okay, here the wall separating the system and the surrounding is called the adiabatic wall. Okay, so they have changed the ways by which they can do the same amount of work. Okay, they have just one way is that they have changed the temperature, and the second way is they have taken electric work. In the first, they have taken mechanical work. Okay, the change in energy, the change in internal energy is the same in both the cases. So there is no difference in the work done, but the kind of work is different. Okay. So the experiments of J.P. Joule, he was able to show that given amount of work done on the system, no matter how it was done, produce the same change in state. So the amount of work is relevant, not how it is done. The second term is heat. We can also change the internal energy by transfer of heat. Okay, and heat is usually called, heat difference is usually denoted by Q. And apart from adiabatic wall, all other walls and all other systems can transmit heat. If Q is positive, heat is transferred from the surroundings to the system. Q is negative, heat is transferred from the system to the surroundings, right? So if you don't change temperature, then you can't do any work. And if you're not doing work but still changing the internal energy, then there is only one possible way, that you have given in heat or you have taken out heat, right? So in the general case, the change in internal energy is equal to sum of heat transferred and sum of work done. Okay, both of these you add with appropriate sign. Okay, you have to put the appropriate signs and you get this equation, and this equation is known as the first law of thermodynamics. It states that the energy of isolated system is constant. You can only change this energy by transferring energy or heat from the surrounding. It is commonly stated as the law of conservation of energy. Energy can neither be created nor destroyed. Next, we go to the practical applications of the first law. Okay, work. Let us concentrate on the nature of the work. For understanding pressure volume work, they have given you a cylinder and they have moved the piston from initial volume to the final volume, and this is the amount of distance they have covered. The pressure change, they have put an external pressure which is P external, and that external pressure was able to move the piston till a distance L, right? Okay. Volume change, L into area of cross section. Pressure is force upon area, we know that. So force on piston is pressure into area. Now work done is force into distance, and force is pressure into area, right? And volume change or distance is volume change by area. So we put all of these, we get this. This is the final equation. P external into change in volume at a minus sign. So what does the negative sign show? It says that it indicates that compression work is done on the system. Okay, it will be negative when the system is doing work, because we have to add a negative sign. If the compression is happening, then work is positive. If expansion of the system is happening, work is negative, because system itself is doing work, so it will lose some energy. At an integral case, we can just use this formula, right? Work is equal to integration of minus P external dV. Limit is final to initial to final volume. Now they have given a definition of reversible process. Okay, so this is an irreversible process because there are discrete steps and you cannot come back. But at a reversible process, it is continuous throughout and you can trace it backwards at any point of time. For reversible conditions, we have an integral, and for irreversible conditions, we just do simple arithmetic, right? For reversible condition, we have one more formula of work. This is the work of a reversible condition, and manipulating it by using the gas law, we have a few more formulas. Work, the reversible work is equal to minus nRT ln Vf by Vi, or integration of the derivative. Okay. And if we change it into the logarithmic scale, we will get minus 2.303 nRT log Vf by Vi. What is free expansion? Free expansion is expansion of a gas in vacuum. Here, work done is equal to 0. Work done is equal to 0 because P external is 0. P external is 0. So work done is 0. Then isothermal and free expansion of an ideal gas. For isothermal irreversible change, this is the work done. Irreversible means simple arithmetic. Then for isothermal reversible change, okay, reversible, we have to use the integration and log ka scale here. These are all the values of heat, okay? Because at isothermal delta U is equal to 0. If delta U is equal to 0, then Q is equal to minus W. That is why in here there is no minus ka sign in front of 2.303, because it is equal to minus W. So definitely the minus sign will get cancelled. We have the formulas for heat also now. Okay. Right. So what does all this, how to remember all this and all? I'll just tell you one simple formula. First formula which you need to remember is delta is equal to Q plus W. Next, you need to remember is W is equal to minus P external delta V. This is irreversible, and minus P external dot dV, and you have to put the limits of V initial to V final. This is irreversible. This is reversible. Right. For a general, okay, there are some few processes which you need to know. There is isothermal. What you need to remember here is delta U is equal to 0. Delta H is also 0 here. Then there is adiabatic. Adiabatic, Q is equal to 0. The last one is free expansion. P external is 0, therefore W is equal to 0. And isovolumic, here also work done is 0 because there is no change in volume. Right. So these things you need to remember. ISO, the most cumbersome one is isobaric, because in this nothing is 0. So Q plus W is equal to delta U. All of these are, you need to calculate each of them separately. That is a bit difficult, and if a reversible isobaric is asked, that is even more difficult because you have to do integrations and all. Right. So we have done isothermal, we have done free expansion, we have done adiabatic, right? Okay. Let's move to enthalpy. After enthalpy, what do we have? We have extensive and intensive properties. And after it, I think most of it we are done only. Okay, we'll just see why do we need enthalpy. So we know that what internal energy is. See, internal energy is the basically all the energy that is present in a compound. Okay. All the energy that is present in the compound is internal energy. It can be mechanical energy. It can be any kind of, physical, chemical, mechanical, all kinds of energy are internal energy. But the heat absorbed at constant, see, the internal energy you can determine by Q plus W. But suppose the heat energy absorbed at constant volume. Okay, so if volume is constant, then work done is 0. Then the change in internal energy, it amounts to just the heat, whatever heat has been transferred. Most of the chemical reactions, however, are carried not at constant volume but at constant pressure. That is the catch here. Constant atmospheric pressure. So we need to define another state function which is suitable under these conditions. We may write equation 6.1, the first equation, in which work has been replaced by P delta V. And at constant pressure, the heat is absorbed as QP. Okay. And P delta V, yeah, it represents the expansion work by the system. Let's rewrite the above equation. On rearranging, we find that the QP, or the heat absorbed at constant pressure, is something in which the internal energy is getting added with your pressure volume work, right? Your pressure volume work is being added to your internal energy. That is why we just, for convenience, nothing else, for our convenience, we define another term, another state function, which is the enthalpy. We define another term, which is the enthalpy. And by definition, the enthalpy is equal to internal energy plus pressure volume. And if you put a delta, then you need to, what I'm saying is, if you put a delta H, then you need to put a delta U plus delta of PV. So this is a bit complicated because only pressure here is constant, volume is not constant. So delta P is what? Delta P is 0. So we can directly write delta H is equal to delta U plus P delta P. P is the constant pressure, right? This is the enthalpy. Now we need to see when it is positive and negative, then we can move ahead. The delta H is negative for exothermic reactions, which evolve the heat during the reaction, which is very, you can easily determine from using a bit of common sense. This is reactants, and they change into products and give out heat. So if the reactants are having enthalpy H1 and the products are having enthalpy H2, heat has also been released. All of this is constant pressure, and we know that heat released under constant pressure is nothing but enthalpy. So we name this H3. Definitely H1 will be H2 plus H3. And if we just ignore the H3 here, we just see the enthalpies. So H1 minus H2 will be positive, but H2 minus H1 will be negative, which is final minus initial. That is negative. So delta H is negative for these reactions, right? Okay. Delta H is positive for endothermic reactions, which absorb heat from the surroundings. At constant volume, this equation becomes something like this. Okay. The difference between delta H and delta U is not usually significant for systems containing only solids or liquid. Solids, and why? Solids and liquid do not suffer any significant volume changes. So if there is a system in which there is only solid or liquid, there are no gases involved, you can simply write delta H is equal to delta U. Why? Because the volume change is irrelevant. Solids and liquids are incompressible. They cannot change their volume effectively. You can simply say ki the enthalpy is equal to the internal energy here. There is no pressure volume change work involved. Okay, let's move on. We move to extensive and intensive properties. What is an extensive property? Extensive property is whose value depends on the quantity or size of the matter present in the system. For example, your best example is volume and mass. Okay. Even your internal energy, enthalpy, heat capacity, all these depend on the amount of matter. So if amount of matter is more, your mass will be more, your volume will be more, the internal energy that it is holding is also more. All of this depend on the amount of matter present in the system. They are extensive. Then we have something called intensive properties. Okay, they are not dependent on the quantity or size of matter present in the system. Okay, examples are temperature, density, pressure. So how to, okay, I'll try to make it easy for you. Let us take a system. Okay, we have some amount of this. The system has volume Vi, okay, pressure Pi, and temperature Ti. All right. Right. Now what we do is we just put a division in between the system. The volume of this part will be Va. The volume of this part will be Vb. Volume has been changed. So it is extensive. But just putting a partition, does it change the pressure and temperature? No, we have not compressed the total container. We have not heated or we have not done any work on the container. So pressure and temperature are still the same. They are intensive properties. They are not dependent on the amount of matter present in the system. Although, yeah, volume, see, we have just half. If we half it, then half of the moles of the gas will be here and half of the gas will be in the other compartment. The ones which depend on this, they are extensive. The others are totally intensive. Next, heat capacity. What is heat capacity? Heat capacity is that thing, but this coefficient which we are multiplying with the change in temperature to get the heat. The magnitude of the coefficient depends on the size, composition, nature of the system, and it is called the heat capacity. What is heat capacity? By definition, heat capacity is the amount of heat required to, C is the heat required to change temperature of a fixed substance or fixed amount, or appropriately we can say given amount of substance by 1 degree Celsius or 1 Kelvin. So to change the, suppose you have been given a tumbler of water and you want to increase the temperature of that tumbler of water by 1 degree Celsius. So amount of heat that you will give the tumbler of water for increasing its temperature to 1 degree more, it is the heat capacity of that tumbler. And if we divide the heat capacity by the number of moles, it is called the molar heat capacity. If we divide the heat capacity by the weight of the substance or by the mass of the substance, then it is called the small c or specific heat capacity of the substance. Okay. So we know molar heat capacity and specific heat capacity now. So molar heat capacity is the total heat capacity divided by number of moles in the system. Specific heat capacity is the total heat capacity divided by mass of the system. Next, we move between the relationship between Cp and Cv. So what is Cp and what is Cv? Cp means heat capacity at constant pressure. Cv is heat capacity at constant volume. Now, at constant volume, Qv is Cv delta T. At constant pressure, Qp is Cp delta T. And Qv and Qp, what do they denote? Qv is delta U, Qp is delta H, because at constant volume, delta U is equal to delta H. The difference between Cp and Cv, if we subtract Cp and Cv, we get this. We subtract Qv from Qp, and here we take Cp and Cv common. After doing all these calculations, we put the values of delta H and delta U in this, and we get this equation. Cp minus Cv is equal to R. This is a really important relationship which you need to remember. Measurement of delta U and delta H, calorimetry. So what is calorimetry? Calorimetry is study of change in heat, study of work done, heat involved, and all of that. To do calorimetry, we need a calorimeter. Usually a bomb calorimeter is involved, in which the volume is constant. Okay, and we can easily measure the temperature change. Next, let's see how delta change in internal energy is measured. So delta U measurements, nothing. Heat absorbed at constant volume is measured in a bomb calorimeter. A steel vessel is immersed in a water bath. The whole device is called a calorimeter. The steel vessel is immersed in water bath to ensure that no heat is lost to the surrounding. So whatever reaction you are doing, you're doing some reaction here, which I have underlined by green, and it will release some amount of heat. Okay, this heat will get transmitted first to this steel box, and from the steel box it will get transmitted to the water which is surrounding the steel box. So the water will get heated, water will heat up. All this change in temperature of water will be recorded by this thermometer. Okay, we have a thermometer here. This thermometer will record the change in temperature, and we can easily find out how much energy has been involved by using the heat capacity of the water, which we know. Delta H measurements. So measurement of heat change at constant pressure. Here we don't need to seal the calorimeter. We just take an open polystyrene cup and we just record the temperature. Pressure, it is left to the atmospheric pressure. Okay, right. Next, we move to the topic enthalpy change, or delta H of a reaction. So if a reaction is proceeding and it is proceeding in this direction, reactants to products, the change in enthalpy is known as the reaction enthalpy and is given by delta HR. And change in enthalpy is the sum of enthalpies of all the products minus the sum of enthalpies of all the reactants. But first, you need to balance the chemical equation. Okay, so on balancing the combustion of methane, we get this reaction, and the change in enthalpy is something, it looks something like this. Okay, and you measure the molar enthalpy or specific enthalpy, whatever you need, but it should be the same for all the reactants and products. Now, enthalpy change is a very useful quantity. Knowledge of this quantity is required when one needs to plan the heating or cooling required to maintain industrial or chemical reaction at a constant temperature. Right? I'll tell you what it means. It means key, suppose the delta H comes out to be negative. What does it mean? It means that the reactants are getting converted into product and liberating some heat. Right? They are liberating some heat. So how do you ensure that the products are continuously formed from the reactants? You will try to bring down the temperature. You will make it more cold so that reactants give out more heat. Reactants give out more heat. They are converted into products more faster. Okay. The product is, you're getting a stable supply of product by decreasing the temperature. So you need to know whose delta H is negative, which reactions delta H is positive. All these things you should know. Next, enthalpy changes during phase transformation. Phase transformation is what do you understand from phase transformation? It is like a solid is getting changed to liquid. At a phase transformation, the temperature is constant. Okay, the temperature remains constant, but heat is involved. So, for example, ice to water, the melting takes place at constant pressure. Temperature remains constant. Okay. This is the reaction which they have given, and the enthalpy of fusion is defined as this delta H fusion. Definition: the enthalpy change that accompanies melting of 1 mole of solid substance in standard state is standard enthalpy of fusion or molar enthalpy of fusion. Melting of a solid is endothermic, so all enthalpies of fusion are positive. Why? Because melting is always endothermic. So all enthalpies of fusion are positive. Now, enthalpy of vaporization is amount of heat required to vaporize 1 mole of liquid at a constant temperature under standard pressure of 1 bar, and it is called standard enthalpy of vaporization. It is also positive. Standard enthalpy of sublimation, again, enthalpy change when 1 mole of solid is sublimed at constant pressure of 1 bar. So for all phase phase transformations, one thing is there: pressure and temperature are constant. Okay. Next, standard enthalpy of formation. The standard enthalpy change for the formation of 1 mole of compound from its elements in their most stable form. So this is an important point. The constituent element should be in their most stable states of aggregation. You cannot just take any carbon and any oxygen and create carbon dioxide and calculate its enthalpy of formation. You need a particular form of carbon, a particular form of oxygen to do that, which is called the reference state. So for these reference states, for example, for carbon, the reference state is graphite. For oxygen, it is just the oxygen gas. For sulfur, it is the rhombic sulfur. So what is so special about these reference state is that their own delta H formation is, the enthalpy of formation is 0 for all the standard reference states. Okay. So that when you are, you have measured a change, you have measured a heat change during the reaction. Suppose carbon graphite, when it combines with hydrogen, it gives methane and some amount of heat. You have measured this amount of heat. According to this, heat is something called an enthalpy. According to your this thing definition, Q at heat change at constant pressure is the enthalpy only. And you have measured some heat. Some heat you have measured, which should be equal to the enthalpy of CH4 minus the enthalpy of graphite and the enthalpy 2 times the enthalpy of hydrogen. And we know that carbon, graphite and hydrogen gas are reference states, so they will be 0. So if we are defining this change in heat as heat of formation or enthalpy of formation, So enthalpy of formation of CH4 is whatever heat change we have just encountered. That is why we need to do it with the reference state so that we can just cancel their enthalpies as 0. Now they have given a table in which molar enthalpies are given, right? Then we come with the thermodynamic equation and Hess law. What is Hess law? Hess law says that if you need to change a substance A into B and you have observed the enthalpy changes delta H of reaction, it means that if you travel from an alternate path A to C, C to D, D to B, you do the same thing but in an alternate path and you get delta H R1, delta H R2 and delta H R3. At the end, delta H R will be the sum of these delta H R1, delta H R2 and delta H R3. This is Hess law. Whatever path you follow, if the initial and final products are same, then the enthalpy change should be same. Now we have already seen, okay, just as enthalpy of formation, there is an enthalpy of combustion, which is defined as when a thing is burnt in complete oxygen. Okay. Enthalpy of atomization, it is the process of converting a substance into its constituent atoms in gaseous state. That is enthalpy of atomization. Then bond enthalpy, definitely it is the energy released when bond is dissociated. Enthalpy of solution, it is the enthalpy change when 1 mole of the amount is dissolved in a specific solvent. All these are really easy to understand. Lattice enthalpy is, the energy released when gaseous constituents of the ionic compound, they form a solid lattice. Okay. Enthalpy change, which occurs when 1 mole of ionic compound dissociates into a gaseous state, or you can just say gaseous ones become a solid. You can go to the reverse also. This is enthalpy. Okay, we are done with today's topics. The spontaneity and all will cover from tomorrow. Entropy and all. Okay. Right. Let's move on to let's solve some previous year questions now. This is something related to the work done. So work done, we know that work done is minus P external delta V, irreversible, and integration of P dV for reversible. Here we can just see that a work like this has been done. And it is an ideal monatomic gas. Yeah, we just need to find out the area of this curve under the PV graph and we'll get the work done. So let's try to find it out. The pressure involved is 1 and the volume change is 20 liters and this is 1/4 of a circle. Okay, this is 1/4 of a circle. Pi, and we have to multiply it by 100 to convert it into joule. It is something 500 pi joules. Next, an athlete is given 100 gram of glucose for energy. This is equivalent to 1800 kilojoules of energy. 50% of this energy gained is utilized by the athlete for his sports activities in the event. In order to avoid storage of energy, the weight of extra water he would need to perspire is. Assume there is no other way of consuming the stored energy. The enthalpy of evaporation of water is 45 kilojoules per mole. So he has total 1800 and he has spent 50%. So he is left with 900 kilojoules of energy. Now he needs to perspire water, or he needs to evaporate some amount of water with this energy so that it is not stored. So 900, okay, the enthalpy of vaporization of water is 45 kilojoule per mole. So to vaporize 1 mole of water, you need 45 kilojoules. So how many moles of water can he perspire or evaporate with 900 kilojoules? We'll just divide it. 900 by 45. 20 moles of water he needs to perspire. And weight of 1 mole of water is 18 gram. So 20 into 18. 360 gram of water. Right? So this is the answer. Next question says 28 liter of carbon dioxide is produced on complete combustion of 16.8 liter of gaseous mixture of ethene and methane. Ethene and methane. Okay. The heat evolved during the combustion process, they have asked. So let's write the equation first. A gaseous mixture of ethene and methane. First C2H4 is ethene, and we burn it in oxygen to get CO2 plus H2O. 2 CO2, 2 H2O, that means 3 moles of oxygen will be burnt. Next, methane, CH4, is burnt in oxygen to form CO2 and H2, 2H2O, because CH4 is there. This will be requiring 2 moles of oxygen. Now, we know that the total volume initially is equal to the volume of CO2 evolved finally. Okay, because H2O will be liquid at this temperature and pressure. Whatever volume is final, it is of CO2, which is 28 liters. Combining these two equations, wait, we can't combine it like that. Let us assume that X of ethene has been used. X liter of ethene has been used. How many liters of CO2 will be produced? 2x. CH4, how much CH4 has been used? 16.8 minus X. So how many CO2 will be, how much CO2 will be produced? It is again 16 minus X. This is the amount of CO2 that is being produced. Now we can see it is coming almost, if we add 16.8 is equal to it. The total amount of CO2 evolved is 28 liter is equal to 2x plus 16.8 minus x. So from here x will come to be 11.2 liters. So 11.2 ethene and rest 5.6 methane. This is the composition. They have asked us for the heat produced, heat evolved. They have given us the combustion of ethane and methane and ethene. This is for 1 mole of the substances, or 22.4 liters. If we just calculate for 11.2 ethene, which means 1 by 2, 11.2 liter ethene is 0.5 moles ethene, and 5.6 liter methane is 0.25 mole methane. So the energy changes will be 900 by 4 and 1400 by 2. 225, 700, totally 925 kilojoules of energy has been released. That is the answer. So you need to find out the percentage composition, and using the heat of combustion equation, you can solve this question. Next, which of the following relations are correct? Actually, some of these we have not yet studied, but we'll still try. First says delta U is equal to Q plus P delta V. Do you think it is correct? It should be minus, right? Because work done is equal to minus P delta V. So this is incorrect. Delta G is equal to delta H minus T delta H. I'll tell you, this is correct. Delta S is equal to, okay, we'll just check the D. Delta H is equal to delta U minus delta NG R T. So I think, yeah, this is also correct. So the answer is B and D. When 2 liters of ideal gas expands isothermally into vacuum, which is free expansion, work done is equal to 0. And isothermal, so delta U is also equal to 0. The total volume of 6 liter, okay, it is expanding to a total volume of 6 liter. Oh, already there is a volume change. We should not jump to conclusion. So there is a volume change of 4 liters. It is not a 0 work. The change in internal energy, they are saying, okay, it is isothermal, right? Isothermal, so change in internal energy will be 0. This was a mind bender. Don't need to calculate. Question 6 says 1 mole of ideal gas is allowed to expand reversibly and adiabatically from temperature of 27 degrees Celsius. Work done is this much. Final temperature we need to find out. So it is a adiabatic condition. So delta Q will be 0 because it is adiabatic. So delta U is equal to work done. And delta U is equal to work done. So what all they have given us? They have given us the temperature. They have given us the work done. We need to find the final temperature. And it is a reversible. Is equal to this is the equation of delta. So sorry. This is the equation of delta U. And it is given that it is equal to 3 kilojoule per mole. So mole is 1 minus RT ln T2 by T1. This is not nRT, this is NCV. N is 1, CV they have given 20. Okay. So ln T2 by T1. T1 they have given 300 Kelvin is equal to 3 by 20. We could convert it into log. This is what 10 to the power so T2 is okay, it comes to be around 126 Kelvin. So it's bit of your engaging in calculations. Okay, so we'll continue from here in the next session. Thank you.